Okay, this is another video in the series, What's in the Bleakin Beaker. And this one is hydrolysis. And remember, hydrolysis is just a reaction of a salt with water. Now, not all salts will react with water. Salts that are made from a strong acid or strong base don't hydrolyze. Their pH will be 7. But salts that do react with water, the reaction is called hydrolysis. It is one of our 4 types of equilibrium. This one I'm going to give you is a beaker filled with sodium fluoride. So we know when the salt is dissolved in water, it dissociates into a cation and an anion. Now, sodium is a conjugate acid of sodium hydroxide, which is strong, so sodium ions spectate in aqueous solutions. But fluoride is the conjugate base of a weak acid, hydrofluoric acid. And so conjugates of weak acids will hydrolyze. Conjugates of weak bases, such as ammonia, is a weak base. So anytime you have its conjugate, which is ammonium ion, is the conjugate acid of this weak base, it will hydrolyze. So any conjugates of a weak acid or weak base will hydrolyze. So to write the reaction, you take fluoride ion, which is the conjugate base of the weak acid, hydrofluoric acid, and let it react with water. Since it's the base, water acts as the acid. Donating the proton, you get hydrofluoric acid plus hydroxide ion. So don't let hydrolysis throw you. It's still going to be a Bronsted-Lowry acid-base reaction, and you're going to have to generate a rice table. So the first thing to do is figure out which ion of the salt is reacting, let it react with water, let the acid donate the proton, and predict your products. Initial. So to do your initial row of the table, I need to tell you the concentration of that salt that's in the beaker, sodium fluoride, and I'm going to say it's 0.25 molar. So when the sodium fluoride dissociates, you realize that you get 1 mole of fluoride ion for every mole of sodium fluoride. So the concentration of fluoride is simply 0.25 molar. It's also the concentration of sodium ion, but sodium ion is not in my reaction. So for initial, we have 0.25 molar fluoride ion. Ignore water. We don't have this initially because the only thing in my bleakin beaker is the salt, sodium fluoride. Now, some of the fluoride will react with water. We call the amount that reacts X. They're in a 1:1:1 mole ratio, so if X reacts, it forms X hydrofluoric acid and X hydroxide. At equilibrium, you have 0.25 minus X, 0 plus X is X, 0 plus X is X. And so you have a rice table like you're used to for a weak acid dissociation or a weak base. The thing that makes hydrolysis tricky, I think, for students is in this next step. Because we always, after generating a rice table, write our equilibrium constant expression, because we are at equilibrium. And it's the concentration of the products raised to their coefficients, which are 1, divided by reactants raised to their coefficients. Omitting pure solids and liquids. Water's a pure liquid. We don't include it in the equilibrium constant expression. Now, this part's not tricky because you've been writing equilibrium constant expressions for a while. What makes it tricky is what K to plug in. Usually, you will be given the K value for the weak acid or the weak base, you'll be told that the Ka for hydrofluoric acid is 7.4 times 10 to the negative 4. All right, but we don't have hydrofluoric acid in our reaction. We have its conjugate base. And so you have to remember that the product of the equilibrium constants for the acid and its conjugate base always equal the Kw for water. So anytime you're looking for the conjugate base of a weak acid, you're just going to take the Kw for water and ratio it to the K of the acid it comes from. And so we can replace this K with a ratio. But the students, you've really got to look when you get to this part of the problem, because the tendency is, oh, they gave me a K. Okay, there it is. Let me plug it in and start solving and I'll get the wrong answer. No, do not do that. Make yourself look, stop, and go back and see what K they gave you. Did they give you K for this? Plug it in. But they didn't give you the K for that species. They gave you the K for its conjugate acid, HF. Therefore, before I can plug that value in, I must plug it in as a ratio. Kw over K of the acid HF. So when I do that, I'm going to end up getting the K, we're going to call it a B because this is a base. Kb is going to equal the Kw for water divided by the Ka for the acid. And that is going to give me a value of 1.4 times 10 to the negative 11. And that's the K I need to plug in. So this is where most students miss it. If they miss hydrolysis, it's because they get confused on what K to plug in where. Let your reaction be your guide. You need the K for whatever's here, reacting with the water. If it's F minus, and they give you this in the problem, plug it in. But if they give you K for HF, then you have to do the ratio to get the hydrolysis constant. And then we end up with 1.4 times 10 to the negative 11 equals x times x over 0.25 minus x. Solving for x, what does x equal? Well, x equals hydroxide ion concentration, which is 1.4 times 10 to the negative 11 times 0.25. And then take the square root of that, and we get 1.9 times 10 to the negative 6, and that's a molarity. Now, why did I ignore this x? Look how small. Hydrolysis constants are very, very small, much smaller than the equilibrium constants or dissociation constants for a weak acid or a weak base. So you're always going to get to make the assumption that X is very small compared to the initial concentration of the ion from the salt. And if you see, if I take 0.25 and subtract X, you see I'm going to end up still with 0.25. So it is a valid assumption. This is now the hydroxide ion concentration, so go back and reread the question. That's another, cautionary spot students miss because they're so involved in trying to figure out what the heck to do in the problem that they forget, they lose track of what was the question actually asking me for. So if it's asking me for hydroxide ion concentration, I'm done. If it asks me for pH, I can get the pOH using this number and subtract from 14 to get the pH. Or it may just be asking me for the hydronium ion concentration, in which, if that's the case, there's a simple relationship between the hydronium ion concentration and the hydrogen ion concentration, and that is simply that the product of the two concentrations, hydronium ion concentration and hydroxide ion concentration in an aqueous solution, is always equal to Kw. That's the product. So the concentration of hydronium then is going to equal Kw divided by hydroxide. So when I plug my numbers in for that, I'll end up with a hydronium ion concentration of, and I will take that and get 5.3 times 10 to the minus 9. Concentration, always put your unit on it. So there we have it. And that's how to do hydrolysis when you're left with a, when the conjugate base, when the anion of the salt reacts with water.